Humphrey Davies was the first to isolate potassium from potash. Potash can be mined out of the ground, or it could be isolated from the remnants of burnt wood. He used something that was new to his time, electrochemistry. He first melted the potash and then used the biggest battery he had to run electricity through the melted potash. The electricity separated the components, and potassium was isolated to one of the electrodes. You see here the potassium being isolated. Today we mine the potassium out of the ground. We have large facilities that have various support structures and buildings. We dig deep into the earth in giant shafts, and as we dig these shafts, we dig elevators that are large enough to take down vehicles. As the vehicles obviously transport the miners, but they also transport these giant mining tools called borers, and they break up the potash. Once isolated, potassium is very reactive and has to be kept in oil. You can take it and you can see how reactive it is by wiping off the oil and setting it in water. It's actually very explosive. Potassium's reactivity stems from its single electron in its outer shell. Potassium is quick to get rid of this single electron so that its outer shell can be filled. Here you have a very simplistic model of the atom showing the outer electron in the outer shell waiting to be released. If we take a look at potassium, we know it has 19 protons and a mass number of 40. The mass number 40 tells you that you have 21 neutrons and 19 protons. The 19 comes from its atomic number. Remembering that these 19 protons, in order to have an electrically neutral atom, is going to require the atom to have 19 electrons. And it's these electrons that drives the chemistry of potassium. Let's take a look at what the orbitals look like. If we drop the nucleus down to a very tiny dot here in the middle of this green canvas, and we draw the first two electrons in the outer shell, in its 1s, in the 1s shell, you can see it's sort of a haze, an electron cloud there around the nucleus. After the 1s is filled, the 2s fills in, so there's two more electrons, and here you have a diagram demonstrating how many electrons are in each of the orbitals. So we have the 1s is filled, the 2s then gets filled, that's 4 electrons. Then we have to worry about the 2p. The p's relegate themselves to the 3 axes, the x, y, and z, 2 electrons on each of the axes, and they form these sort of dumbbell shapes. The next energy level to be filled is the third energy level, and of course the electrons will start filling in the 3s, which means 2 electrons will surround the 2p orbitals further out, and then the 3p shells start to fill in. The 4s is actually lower in energy requirements than the 3d, so it's that last little electron, that 19th electron, finds itself in the 4s all by itself. Now remember, in the octet rule, atoms become more stable when they have a full octet. So this atom, having only 19 protons, incapable of pulling in the electrons necessary to fill its octet, is more than willing to release its single electron and allow another atom to fill its octet with it, forming an ionic bond. So this is the reason that potassium is so reactive. It so easily releases that electron and becomes more stable, finds a lower energy state. And when it finds that lower energy state, it has to release all that extra energy it had, and that explains the reactivity of potassium.